which we will discuss about liquid penetrant testing. You are listening to me, Dr. Piniar Wiston, in this video. Liquid penetrant testing is an effective method of detecting surface discontinuities in metals or other non-porous materials. It is widely used in various industries including aerospace, automotive, manufacturing and construction due to its effectiveness and simplicity. It was developed in 1930 and liquid penetrant testing was initially used in aerospace industry. Over the decade, advancements in penetrant formulation and application techniques have enhanced its effectiveness and versatility. Penetrant testing utilizes the natural accumulation of a fluid around a discontinuity to create a recognizable indication of a crack or other surface opening defects. Capillary action attracts the fluid to the discontinuities as compared to its surroundings. LPT detects flaws that are open to the surface like cracks, seams, laps, lack of bond, porosity and cold shunt, etc. It is very effective in inspection of ferrous metals, non-ferrous metals, non-porous, non-metallic materials like ceramics, etc. This method is widely used for testing of non-magnetic materials. So the principle of liquid penetrant testing is the penetration or the ability of a liquid to wet the surface of a solid workpiece or specimen and flow over the surface to form a continuous and reasonably uniform coating, thus penetrating into cavities that are open to the surface. The ability of given liquid to flow over a surface or enter surface cavities through the mechanism called capillary action is utilized in liquid penetrant testing. So, the developer material in conjunction with visual inspection reveals the surface flaws. So there are two components which will be in use during liquid penetrant testing, namely the penetrant and developer. Penetrant is a liquid capable of testing the entire surface and being drawn into the opening. Usually it is a brightly colored eddy or paint or fluorescent material which will be used as penetrant. Whereas developer is an absorbent material which is capable of drawing traces of penetrants from the cracks back onto the surface. The second step in the inspection process is the application of penetrant fluid to the cleaned surface. The fluid should spread freely and evenly over the surface and move into the cracks. The application of penetrant may be achieved by dipping the component in a bath or of penetrant liquid or by spraying or brushing. The minimal dwell time of about 20 to 30 minutes may be allowed after penetrant application. Larger period may be necessary in certain circumstances. Step 3 is removal of excessive penetrant. This is the most important step in the entire procedure. The desired result is that the surface is completely clean of penetrant, yet the crack or defect retains all the penetrant that enters into it. Excess cleaning may remove the penetrant from the upper region of the defect, with the result that the developer does not reach the penetrant or no defect is indicated. The next step is application of developer. After removing the excess penetrant, a thin coating of developer is applied over the surface to draw the penetrant out of the crack and increase its visibility. Another important function of the developer is that it covers the surface with a color that provides good visual contrast to the penetrant. This increases the visibility of a defect. The next step is inspection and evaluation. The last step in the process is the scanning of the surface for indication. The scanning may be carried out using visible light conditions or ultraviolet or laser incident light, and the defect recognition may be made with human eye or automated optical scans. Each indication that appears should be evaluated. The advantages of liquid penetrant testing include the ease of use. The testing process is straightforward and does not require complex equipment. Technician can be trained quickly to perform LPT. The cost effectiveness, like compared to other non-destructive methods, LPT is relatively inexpensive. The equipment and materials required are often affordable. The high sensitivity of LPT. LPT can detect very small surface defects, often as small as 0.001 inches, which is 0.025 millimeters, and making it highly sensitive. It is versatile application. It is applicable to a wide range of materials including metals, plastics, ceramics, effective for various shapes and sizes of the component, and the results are immediate. LPT provides quick results allowing for prompt decision making regarding the integrity of components. Then the limitations. It can only detect flaws that are open to the surface, and it cannot be used for porous and rough surfaces. Surface breaking defects like internal flaw detection are unsuitable to be detected through LPT. The surface preparation. Effectiveness of LPT relies heavily on the cleanliness of the surface. Contaminants such as oil, dirt, or paint can interfere with the penetrant's ability to enter defects, leading to false negativities. Material compatibilities. Not all materials are suitable for LPT. Highly porous materials or those that react to the penetrant may yield unreliable results. Compatibility testing is essential before conducting LPT on new materials. Skill and training requirements. While process is straightforward, accurate interpretation of results requires skilled technicians. Proper training and certification are necessary to minimize the risk of misinterpretation. Some penetrants and developers may contain hazardous materials which must be handled with precautions and with necessary handling, storage, and disposal practices. Applications of liquid penetrant inspection include inspection of tools, dies, tanks, vessels, reactors, piping, dyes, and pumps in the chemical, petrochemical, food, paper, and processing industries. Diesel locomotives, truck and automobile parts, aircraft engine parts, propellers, wing fittings, casting, and so on. So the sequence of operation in liquid penetrant testing include cleaning, penetrant application, removal of excess penetrant, application of developer, then followed by inspection and evaluation. Dwell time is the amount of time required for a penetrant to move into the crack. Penetrant materials is a mixture of an indicating dye, which is a tracer, and a carrier fluid, which is a vehicle fluid. A good penetrant should possess the ability to penetrate discontinuities quickly and completely. It should be easily drawn into discontinuities by capillary actions. It should not evaporate or dry rapidly. It should be non-flammable, odorless, non-toxic. It should possess stability under conditions of storage. One of the significant factors in choosing penetrant materials is detection sensitivity. Dyes used in liquid penetrant testing can be broadly classified into two main types, namely visible dyes and fluorescent dyes. Visible dyes are color dyes that can be seen under normal lighting conditions. The most common visible dye used in LPT is red, which provides a strong contrast against the surface of the material being tested. Whereas fluorescent dyes are designed to emit light when exposed to ultraviolet light, making them highly visible even in low lighting conditions. These dyes are typically green-yellow in color and are used in conjunction with UV light during inspection. High sensitivity is observed in fluorescent dyes compared to visible dyes, which make them capable of detecting small defects. On the basis of removal methods, dyes used in liquid penetrant testing may be categorized into water washable dyes, solvent removable dyes, and post emulsifiable dyes. Water washable dyes can be removed from the surface using water. They are convenient for inspection where water is readily available and can simplify the cleaning process. Solvent removable dyes require use of solvent for removal and often used in environments where water is not suitable, but they can be more hazardous due to the use of chemicals. Post-emulsifiable dyes require treatment with the emulsifier before rinsing with water. This method allows for better control over the removal process and can improve the sensitivity of the specimen. Based on the sensitivity levels, fluorescent dyes can be often classified, which indicate their ability to detect defects of various sizing. Sensitivity level 1 is suitable for detecting large defects. Sensitivity level 2 is suitable. Moderate sensitivity for smaller flaws. Sensitivity level 3 is high sensitivity, capable of detecting very fine defects. Sensitivity level 4 is the highest sensitivity used for critical applications where even smallest flaws must be identified. Developers. Developers are essential in liquid penetrant testing process as they draw the penetrant out of surface breaking defects, making them visible for inspection. They come in various forms including dry powders and wet solutions and are chosen based on the requirement of the inspection. There are three types of developers, namely dry powder developers, wet developers, post emulsifiers. Dry powder developers, they are typically white powders that are dusted onto the surface after the excess penetrant has been removed. They act as blotter, drawing the penetrant out of the defects and creating visible indications. Dry developers are easy to apply and are commonly used due to their effectiveness and simplicity. Wet developers are applied as liquid spray and can provide a more uniform coating over the surface. They are particularly useful in situations where dry powder may not adhere well to the surface. Wet developers can also enhance sensitivity by allowing better penetration of the developer into tight defects. Post-emulsifiable developers are required in application of emulsifier after the penetrant application. The emulsifier helps to remove excess penetrant while retaining the penetrant within the defect. This method is beneficial for achieving higher sensitivity and is often used in critical applications. Functions of developers. The main functions of a good developer include indication development, contrast enhancement, and dwell time. Developers facilitate the extraction of penetrant from defects, creating visible indication that can be inspected. The indications produced are larger than the actual defects, enhancing visibility. Developers create high contrast environment between the penetrant and the developer, making it easier to detect flaws during inspection. After application, developers require a specific dwell time to allow the penetrant to migrate to the surface. This time can vary depending on the type of developer and the nature of the defects being inspected. Before considering a developer, the following properties are to be considered. Number one, material compatibility. The developer must be compatible with the material being tested. The second point is sensitivity requirements, which is depending on the sensitivity, the choice of the developer may vary. High sensitive applications may require specialized developers. Then the environmental conditions. The environmental conditions like wet developers may be preferred in humid conditions to ensure proper adhesion. Cleaners. Cleaners play a vital role in LPT process, ensuring that the surface is free from contaminants that could mask defects. Proper cleaning is essential for achieving accurate and reliable inspection results. Types of cleaners are solvent cleaners, water-based cleaners, emulsifying cleaners. Solvent cleaners are used to remove oils, greases and other contaminants from the surface prior to the inspection of the penetrant. Common solvents used include acetone, isopropyl alcohol and proprietary cleaning solutions designed for LPT. Water-based cleaners are environmentally friendly and can effectively remove water-soluble contaminants. They are often used in conjunction with water-washable penetrants, allowing for a more straightforward cleaning process. Emulsifying cleaners can be used to remove penetrants that are not water-soluble. They work by breaking down the penetrant and allowing it to be washed away with the water. The factors that must be considered during inspection include indication size and shape, color and contrast, location of indication, comparison with standard, and documentation. The size and shape of the indication provide insight into the nature of the defect. Larger the indication may specify more significant defect, while smaller ones could indicate minor surface flaws. The color of the indication and contrast against the developer background help assess the visibility and significance of the defect. So with this we come to the end of this video. Thank you for listening.